Well, welcome everybody. My name is Simon Nicholson. I'm the co-director of the Institute for Carbon Removal Law and Policy at American University in Washington, D.C. Thanks for joining us today for this webinar. This is one in a series of webinars that the Institute is hosting. You can find other webinars in the series at our website, linked from the bottom of the title page. The webinar today is looking at a new National Academy of Sciences report titled Negative Emissions Technologies and Reliable Sequestration, a Research Agenda. We're joined by two speakers, Steve Pacala from Princeton University, who was the chair of the committee that drafted this report, and Rick Duke with Gigaton Strategies, who was formerly Special Advisor to President Obama on energy and climate issues, to offer his own thoughts about the report. We're going to turn to Steve for about 20 minutes of remarks, and then Rick will have 10 minutes. Any questions that you have for the speakers, please put into the chat box on the bottom right of your screen. We'll turn directly to Steve. Thanks for joining us.
Good afternoon, I guess, everyone. I'm going to deliver a modified version of the kind of presentation that we've delivered when we released this thing to many groups, but specifically in response to Simon's suggestion that the group here is pretty well informed, the audience is pretty well informed, and that a lot of sort of background material is not going to be necessary. So I'm going to go very quickly through background material and loiter over the individual recommendations in the summary. And so those are not visually pleasing, but they have the virtue of being what we actually conclude and recommend. And I'm going to offer some commentary on each one of those. All right, so I want to start with the statement of task, because a report like this doesn't try to do everything. In particular, we did not attempt to investigate any options that would require storing the CO2 in the deep blue sea. And there are many such options, but this report was focused on options where they are land or coastal waters based. There's a bunch of reasons for that we could discuss, but just beware that there exists a whole nother portfolio of potential options for negative emissions that are not covered by it. And so I'll let you read this task statement because it's important to understand that guides everything a committee like ours does. So we were trying to assess the current state of existing technologies for negative emissions, and also the potential for development of them, and then most important, to recommend a detailed research agenda. A detailed agenda to move them forward, and not just to increase understanding or something, but specifically to move them to the point where they could be commercialized at scale. And by at scale, we mean at the scale necessary to solve the carbon and climate problem, which, of course, you have to interpret as gigaton scales, billion metric ton scales. So it's a very, very large scale. So we were fixated on that. We were primarily focused on research efforts that would provide dividends within a decade or so, although there are a couple that would require 20 years to yield dividends. And that was dictated by the time scale of the carbon and climate problem itself. All right, so the negative emissions technologies that we considered can be divided into 5 different hoppers, with one additional, a 6th one, which is sort of an enabling technology. The first one in the upper left-hand corner is, oh, first of all, I should say, just to make certain that everybody's on exactly the same page, right? When we talk about the carbon and climate problem is caused because either through land use or through fossil fuel combustion, we take carbon that was on or underneath the surface of the planet and we introduce it to the atmosphere as carbon dioxide. Negative emissions technologies do precisely the reverse. They take CO2 from the atmosphere and put it on or underneath the planet's surface. So it's the exact inverse of fossil emissions. So the first of these hoppers is coastal blue carbon. coastal ecosystems are really interesting because they continually store carbon in organic sediments that look kind of like peat, that just keep building up and building up and building up. And they basically never saturate. And so per unit area, they have the capacity to store an enormous amount of carbon. And there are various ways to do coastal blue carbon. The simplest and most widely recognized way is to restore coastal wetlands. And there are all kinds of co-benefits for doing that, but these include mangroves, salt marshes, seagrass beds, and so on. The second hopper is terrestrial carbon removal and sequestration. This is the most familiar of the buckets because it includes forestry, afforestation, and reforestation, planting trees which eat carbon dioxide for a living and store the carbon on the ground, and also changes in forest management. For instance, lengthening the rotation period between harvests causes the forested lands that are being managed and harvested to gain mass as the average age of the stand goes up. It also includes agricultural soils carbon storage. In croplands and pastures, the health of the soil, its productivity, water holding capacity, nutrient use, nutrient retention, depends to a significant extent on the amount of carbon in the soil. There's a carbon backbone, which has been lost because of use and misuse in many of our soils. And rebuilding this stores carbon in the soils and also has a lot of co-benefits. Third one is bioenergy with carbon capture and sequestration, so-called BECCS. This is where there are a bunch of different flavors of it, but basically it's biofuels where when the biofuels are combusted, the CO2 that is produced is captured and returned to a geologic reservoir or another reservoir. And so it's like fossil fuel with carbon capture and storage, but with bioenergy, you have the potential to have a negative emission. The fourth bucket is direct air capture, industrial processes that chemically bind CO2 from ambient air and compress it, purify it and compress it, and then inject it into a storage reservoir, usually a saline aquifer, the kind of formations that oil and gas have come from, but potentially a basalt formation. And the final bucket is carbon mineralization. Many people don't know that CO2 is not the bottom of the energy well chemically. There are minerals that CO2 will react with spontaneously and exothermically, right? Without prodding, and to produce carbonate minerals. This is the ultimate fate of CO2 in the atmosphere, although it usually takes a long time. But some of these minerals are highly reactive and have been kept from the atmosphere because they're underneath our feet, right? And within a kilometer of the Earth's surface, there are enough of these minerals it's uncertain, but it looks like to remove all of the CO2 in the atmosphere 1,000 times over. So is it possible to get some of the CO2 in the atmosphere to these rocks, or to get the rocks to the atmosphere? Might be a way to do it that way. And the enabling technology we have here is geologic sequestration. Direct air capture and BECCS depend upon having a place to put the CO2 once you've captured it. And usually this means injecting it into a geologic reservoir. Okay, this table shows what we estimate to be the current state of play. It shows the different options, estimated costs, and then upper bounds for safe potential rate of CO2 removal possible given current technology. Now, the thing to notice, there's several things to notice here. The first thing to notice is that safe means without large-scale land use change that could adversely affect food availability and biodiversity. The committee took really seriously, I think more seriously than a lot of previous studies have, the fact that humanity also needs to double food production in the next 50 years, and that they can't do so by destroying the remaining biodiversity. And upper bound means that with full adoption, all of the land, if you're going to use waste biomass for BECCS, all of the waste biomass of the world is captured. If you're going to do forestry, it's all the forested lands receive the management practices. So this upper bound is really pretty stringent, and one should think of it as at least a factor of 2 too large, because of course it's very difficult to get levels of compliance that large. And even so, what we end up with is an order 10 gigaton upper bound. So one should think about this as a 5 gigaton option, with a lot of that being BECCS, but a substantial amount agricultural soils. 4 options appear to be ready to be scaled up: afforestation, reforestation, changes in forest management, agricultural soils, and BECCS. The first 3, there's a lot of experience with, and BECCS combines a couple of technologies that are pretty mature. And so collectively, these have a capacity, we think, which is like, well, the capacity here is close to 10 gigatons, but that's an upper bound, and a realistic upper bound is less than 5 gigatons. So here are the conclusions. Negative emissions technologies are best viewed as a component of the mitigation portfolio rather than a way to decrease atmospheric concentrations of carbon dioxide only after anthropogenic emissions have been eliminated. This is pretty self-explanatory, and it comes from the observation that negative emissions are just the reverse of fossil emissions. And so it's possible to reduce net emissions of humanity if you have negative emissions technologies. And some of them, of course, are cheaper than mitigation technologies. So for a long time, it is going to be the case that negative emissions are just part of the mitigation portfolio. After a very long time, it is also true that if you wanted to reduce the atmospheric carbon dioxide concentration by more than 100 parts per million, negative emissions technologies would be the only way to do that. But that's a problem for the next century, probably not this one. 4 negative emissions technologies are ready for large-scale deployment. I've already mentioned that. Those are the ones. They'll seem familiar to you, and that's why they're ready for large-scale deployment. Conclusion 3 is that the upper bound on the scale up that I showed you in the previous slide, significantly less than 1 gigaton of CO2 per year in the United States, and significantly less than 10 gigatons of CO2 per year globally. How much, and that's almost entirely because of constraints on available land. Arable land needs to be used for food production. Remaining tropical forest is necessary to preserve biodiversity, and so if you're not going to significantly erode those reservoirs, it really limits how much land you can convert to producing BECCS feedstocks and to afforest and reforest. The one hopper that escapes that constraint is the agricultural soils hopper, because it doesn't require a land use conversion to exercise. So for instance, if you want to reforest, then obviously you're converting land that is not forested, usually in pasture or cropland, into forested land. So it involves a large-scale land use change. Conclusion 4 is comes from a review of the literature. And if you're going to make the goals of Paris, let alone 1.5 degrees, then most scenarios, virtually every scenario that passes the LAF test, has a large role for negative emissions. Think of it as 10 gigatons globally by mid-century and 20 gigatons per year globally by centuries end. That means that we're short. We have 4 options that are ready to be deployed at significant levels, but because of limited per hectare rates of carbon uptake by agricultural soils, and because of competition for food with food and biodiversity for land, the remaining options are going to give us substantially less than 10 gigatons that most of these scenarios have by mid-century, right, 30 years from now, like maybe half. And so where we break reasonably new ground is in the two options that don't have a big place in the marketplace: direct air capture and carbon mineralization. Direct air capture is, as you probably know, now possible. There's a firm, ClimateWorks in Switzerland, that will sell you a direct air capture machine. It looks like a washing machine, and it costs about $600 a ton. But our committee is pretty confident, not certain, but pretty confident, that those costs could be brought down to $100 a ton in the near term. Carbon mineralization is limited by fundamental understanding, but if either of these options could be brought to the marketplace at reasonable cost, they would not be limited in the same way as the existing ones, and so really provide humanity with a very, very useful new tool. Coastal blue carbon is interesting. I'm going to just sweep over it, though, because the amount of land area involved is relatively low. It's an interesting option because we need to do coastal engineering for other reasons, and it's possible to store carbon while doing those, while engaging in those projects for other reasons at zero or even negative, or at least very low cost. But the total amount of carbon that you can get out of it is low because the coast isn't two-dimensional. And finally, we need to understand more about biofuels and more about carbon dioxide sequestration in geologic reservoirs. That would be useful too. And so our recommendation is for a research program that is highly granular to improve the existing options and to make rapid progress on direct air capture and carbon mineralization. And we also have some recommendations about research on biofuels and carbon sequestration that should be undertaken anyway as part of a mitigation portfolio, but would also help the development of negative emissions technologies. I should also say that down the deck there is a granular, which I'm flashing by now, research agenda with, this is the shortened version, but that has costs and dates and durations and individual projects. And so I'm happy to address any of those individual projects as well. But I now want to turn it over to Rick.
There we go. Great, can you hear me? Simon, can you hear me? Can you give me a thumbs up? Okay, great. Thank you for the chance to speak to all of you today. It's a fantastic report. I want to congratulate Professor Pacala and the co-authors on a worthy follow-up to the incredibly important 2015 National Academies report on climate intervention, including carbon dioxide removal. And I want to just say a little bit about some framing questions, a bit on the Beck's questions specifically, then also something about costs and looking ahead to future work. So let me just touch on those all briefly. On the framing questions, I think it's really important that this report moves into defining negative emissions technologies not so much as climate intervention in a way that shades into geoengineering, but more as squarely in the mitigation toolkit. And I think that makes sense, and I think it helpfully clarifies the role of negative emissions technologies, or NETs, in our overall climate efforts. And as Professor Pacala has noted, there is, and as the report underscores, in many ways NETs can be thought of as reversing long-standing, decades-long transfers of CO2 from ecosystems and geologic reservoirs into the atmosphere and putting that CO2 back where it belongs in those geologic reservoirs and ecosystems. And of course, it also cuts CO2 levels in the oceans and avoids the impacts there as well. So in many ways, done right, NETs should not exacerbate ecological risks and should even reduce them in many cases. So as such, and also given, as the report underscores, the fact that as long as we still have GHG emissions globally, a ton of NETs is kind of equivalent in its impact on the climate to a ton of emissions reductions. So for all those reasons, it is fantastic that the report so squarely places nets as an element of the mitigation toolkit rather than in the kind of more murky climate intervention bucket of the original report from 2015. And I think thereby really clarifies the overall framing of the opportunity. I want to just note that, of course, it gets complicated in the details, and the report is clear about the fact that it gets complicated in the details. So the SAFE designation, for example, is something that gets complicated when you start to look at some of the specific opportunities. So how do we think about ecosystem restoration in a changing climate? What does it mean to restore an ecosystem when the ecosystem locations are migrating along with the changing temperature profile of different regions? How do we think about large-scale afforestation, and at what point does that become more of a climate intervention or a geoengineering technology rather than an ecosystem restoration or something that would be, in my view, properly defined as a safe net? And as the report underscores, you get into similar questions around some of the large-scale carbon mineralization questions, where some of that involves so much volume of waste rock and associated potential for contamination that perhaps it should not be considered ecologically safe. And so for these kinds of elements of the NETS toolkit, I would argue that it could be useful to, as a community of folks interested in this, try to, in some sense, put them into a different category than the elements of the NETS toolkit that are the main focus of the report, which are those that are either ecologically beneficial, clearly so, or sort of ecologically neutral, like something like direct air capture with low carbon energy as the source for the related energy consumption. In any event, if this can be done, and if it's possible to broadly define negative emissions technologies in a way that is seen as ecologically benign, then it is quite helpful, because it means that nets can be seen as really, as with all mitigation technologies, things that need to be advanced as quickly as possible, both in terms of innovation and deployment, and the positive synergies between those two projects. And in fact, it can be seen as with all mitigation, strategies that will help us to defer and even ultimately minimize the pressures for resorting to geoengineering ultimately. So those are a few thoughts on the broader framing questions and kind of definitional issues that the report so helpfully clarifies and addresses. Just a quick word on BECCS. I think that the report is very helpful in its recognition that there are real limits on the sustainable biomass supply for BECCS, but also that there are real opportunities for gigaton scale BECCS globally. I think where we need to be, and I should also underscore that the report is extremely valuable in its focus on land use change measurement as a crucial enabling strategy to allow BECCS to scale with confidence and in a way that is actually helpful in terms of climate mitigation. Of course, even with the right measurement systems in place for land use change related carbon fluxes, the key question becomes what policies also are put in place to ensure that the inevitable pressures to use higher productivity lands that actually are competitive with food production are somehow actively managed through policy constraints. Because while I agree that there is gigaton scale potential for truly sustainable biomass supply, including crop residues and forestry residues and the like, I also fear that there will be lots of pressure to produce biomass supply for BECCS markets on more arable land that is in fact directly competitive with food production. So again, we'll need both very strong advances in measurement of land use change and its carbon fluxes, and the report is very clear and very helpful about the potential for integrating field data with remote sensing data to do that better. But we'll also need policies that are forceful and really global in scope to manage through the BECCS process. And I share the fears of many that can easily become counterproductive without both that measurement and that policy progress as part of the BECS scale-up process. Just a quick word on costs. I think that the report is very useful in its focus on things that are quite cost-effective in the sort of under $100 a ton range, and would just underscore that the direct air capture estimates are also in an interesting range in the report. So it seems clear that it is possible, it is feasible for direct air capture to end up costing something like $200 a ton. And just to put that in perspective, you could do 10 gigatons a year by mid-century at $200 a ton for direct air capture, and it would cost you less than 1% of global GDP to make that happen. So not easy to achieve politically, but not beyond the pale either. So very helpful that the report focuses on the low-cost opportunities, but also spells out the real opportunity for longer-term scaled-up use of direct air capture, particularly given that direct air capture avoids all the concerns around ecosystem complexities, permanence, the indirect land use change fears raised by BECS scale-up, etc. So it is crucial that we begin the project now of scaling up the direct air capture element of the toolkit for NETs. And just to double down on that point, if you look at the challenges required to get to gigaton scale for anything in mitigation, they are considerable. And what you see is that take the solar case, solar photovoltaics being the, in many ways, the poster child for success on climate mitigation. And yet, after decades of investment of more than $100 billion in subsidies for solar, all of which I think were well spent, if not always most cost effectively spent, you now are at a point where solar photovoltaics are avoiding perhaps 0.2 gigatons a year of CO2 emissions, even after all of that investment and all of that time. Now, it'll quickly get to a gigaton as solar has now really hit an inflection point globally, but it is, I think, indicative of the scale of the challenge and the amount of time required to really get any kind of net solutions, whether it's direct air capture or, for that matter, the ecosystem restoration opportunities to the gigaton scale, let alone to the 10 gigaton or 20 gigaton scale that the report focuses on. And I'll just also indicate that one of the things that we highlighted in the U.S. mid-century strategy that my White House team pulled together in the Obama administration in 2016 was the same theme in this report, that you really do need nets as part of the package for mitigation even before you have reduced all of the greenhouse gas emissions. And in fact, for decades, we will be seeing some combination of emissions reduction and nets if we're going to be cost minimizing on the way to achieving our warming targets and our mitigation goals. And in fact, in the US mid-century strategy, the cost per ton of abatement triples if you limit the amount of forestry-related and BECS-related emissions reduction potential, and that's common across many different models. But the main point is that is why we need to really begin these two things in parallel. The fact that it takes so long to scale up any mitigation solution, including nets, and the fact that we need nets as part of the package, even as we work as fast as possible to cut emissions. All that means we need to start now and scale as quickly as possible, in my view, across the full range of nets opportunities. And then just to wrap up with some thoughts on future areas of work, and really to then pose a question to Steve about what his view is on future opportunities for additional work. I think it's interesting to look at the questions around what kind of policy development is needed going forward. And as an example of that, you can talk a lot about funding negative emissions through things like carbon taxes. But of course, at some point, your carbon tax revenue will diminish as you successfully eliminate CO2 from the system. So do we need to start thinking about things like negative emissions portfolio standards? Maybe even more important and certainly more urgent is how do we really ensure that the right kind of biomass gets used as we scale up the BECS element of this toolkit. And I've already mentioned all the dimensions of that, or some of the dimensions of that. But let me just close by asking Steve, if I could, the first question, and that would be, what did you leave on the cutting room floor in this process, either because of the scope you were given or because of some other constraint? What would you most like to do next in this general area of NES?
So thank you, Rick. The thing I think that is left undone at the level that our report was aimed is an exploration of oceanic options. All right, so that's simply not been done yet, and you know, the oceans cover most of the land surface, and the oceans are incredibly contentious because we don't understand them, and we can't disrupt oceanic ecosystems in a way that we don't understand, and oceanic biogeochemistry in a way that we don't understand. And it would be very difficult to do also because it requires international treaty, right? You don't have to, you can do what you want with your own land, but you need an international treaty to do something with the oceans. That doesn't mean that we shouldn't look at it, though. And so that's on my wish list. I really hope that some in the funding community would put their heads together and figure out a way to fund a companion NAS study on ocean options.
Steve and Rick, thanks to you both. This is Simon Nicholson again with the Institute for Carbon Removal Law and Policy at American University. We're speaking about this new National Academy of Sciences study on negative emissions technologies and reliable sequestration. Professor Pacala, you gave us just a flip through a couple of slides which laid out a research agenda. And I don't imagine you have time to dig into much of that, but I wonder if you can give us something of the flavor of the research agenda that was recommended by the report. Who was being asked to do what kinds of things?
Yeah, I will do that. The nature of the research agenda depends critically on which technology we're talking about, because they're at very, very different stages of development. So I'll start with direct air capture, which is interesting for some of the reasons I outlined and some of the reasons that Rick outlined. Direct air capture is a technology that, if it could be brought to the marketplace at $100 a ton or even less, would really be a significant game changer. A way to think about that, I think, is to think about liquid fuels. Right now, one of the sectors that's most difficult to mitigate is air travel. You can, in principle, make biofuels for air travel, but there is a demand, there is a projected demand that is very large for air travel at mid-century, and kind of rivals light-duty transport cars today. And the land required to raise those biofuels feedstock is necessary to feed the people when there's a doubling in food demand projected by mid-century. So what to do? And if you had even $100 a ton direct air capture, then each time one sold a gallon of aviation fuel, you could require the capture and sequestration of 10 kilograms of CO2 from the atmosphere. And because of a magic coincidence of units, $100 a ton for CO2 is the same as $1 a gallon for gasoline. And so what you would do is add $1 to the gallon of aviation fuel, what it costs to make room in the atmosphere for it with direct air capture. And that would almost certainly, that bundle would almost certainly beat biofuels on price, but without the same environmental and social externalities that we're trying to avoid. So with direct air capture, the committee was really focused on the need to reduce costs. That's the primary problem. Right now, the only machine you can buy is still expensive, and there are a lot that are promising to bring in prices lower. And the committee actually believes there's high probability that some of them will. But this is a problem in which the number of chemical recipes and the number of physical setups is very large. And the only problem is cost, right? And so this is an area where a startup ecosystem competing over price in a market is the way to make things happen. That's what brought down the cost of wind and solar over a 40-year period. The government subsidized those technologies, created a market, everybody competed for it. And that sort of an ecosystem is really good at driving costs down. We've seen the spectacular results from it. So we have a set of recommendations that are designed specifically to create that ecosystem, but yet also with safeguards to make sure that the information flows back into the overall effort, but while still protecting IP. So direct air capture is sort of special that way. Carbon mineralization is at a very early stage, and the research you'll see there is really academic and fundamental understanding kinds of research, albeit more expensive than a lot of fundamental understanding kind of research because it's expensive to drill holes in the ground and some of the stuff you'd have to do for that. And so that's a sort of a DOE and NSF style operation. The more ready options, the research agenda, is really aimed at improving efficiency, exploring some new ideas that haven't yet been explored, and also a lot of social sciences work aimed at the impact of effective policies, at coming up with effective policies that can at the same time induce landowners to take incentives, which they are historically reluctant to do, and also to prevent the kind of runaway gold rush that Rick was talking about if a price for carbon makes it economically desirable to convert your food raising land into biofuels feedstocks. So in summary, it's a mix of academic research, practical research, social sciences research, and some of it, in particular direct air capture, and some of the BECS works involves a lot of input from private groups, from industry, and from startups.
We have a couple of questions here, Professor Pacala, about in one of the questions, the potential and limitations of carbon utilization strategies. And then a second question about whether biochar found its way into the report and how it was thought about.
Sure. On the utilization strategies, I should say that we, because of the task, were prohibited from looking at utilization strategies. So we didn't spend any time on it at all. There was, though, a compendium or a companion study of carbon capture and use. And so that looked at, for instance, artificial limestones and so on. And that study concluded, as many do, that there are really interesting opportunities here, but also that cost-effective opportunities couldn't deliver all of the needs. So that while it's useful, there's a limit to how much of this stuff you can use. And so we could talk about the particulars of that, but I'd urge you, if you're interested in carbon capture and use, to look at the report that's specifically about that. About biochar, we did have a long, heavy look at biochar. Biochar figures into two of the technologies that are ready now, even though we don't think biochar is quite ready for prime time. Close. One is that biochar is useful to improve the fertility of soils, and it stores carbon in the soils when you do so. It's a question, there are unanswered questions, though, about whether or not adding biochar to soils causes the soils to take up even more carbon, right? Whether there's an additional benefit. There's also in the BECS work an interesting variant of BECS in which you take biomass and you pyrolyze it at about 900 degrees Celsius for just a couple of minutes. Okay, you just sort of flash fire it, and what's left over is a bunch of liquid stuff that looks like crude oil. and can be used like crude oil, refined into liquid fuels like crude oil. But it kind of smells like barbecue, right? Doesn't smell like crude oil at all. And then there's also biochar, which is this pyrolyzed, highly recalcitrant, and quite stable material, which could be in principle sold to farmers and then stored as carbon in agricultural soils where it would improve productivity. So there's a possibility of a win-win there. And if you get the mix right, the biomass, which has been produced by taking CO2 out of the air, the portion of it that goes into the biochar that then gets stored in the surface, that's a negative emission. And although you burn the liquid fuel and put the CO2 back to the atmosphere, there's a component of that that's a negative emission. And the economics of this look really pretty attractive, but there's still a lot of uncertainties about how to do it. So we looked at biochar in both cases and have a recommended research budget for field trials with biochar and for all kinds of work on biochar.
I wonder, Professor Pacala, if you can tell us anything about the reception that the report has had in Washington, D.C. and elsewhere. And then Rick and Professor Pacala, is there anything you can say about what you hope will be done with this report, in particular by the NGO community?
Yeah, so we've gotten what I would call a polite reception from Washington and elsewhere. We released it just before the midterm, which was by design. But as you know, the politics of climate mitigation are complex and divided in Washington right now. Agencies have been really positively we've got a lot of positive feedback from them. I think in part because the recommendations are so granular. There's something that people actually know how to do. Same thing from congressional committees. It's not a bunch of general recommendations and goals, but rather a set of specific research initiatives that could be funded. I think that we have 50 separate line items like that. So that strategy appears to have landed. But of course, the proof will be whether or not any of the money is actually allocated. For the NGO community, I think there's quite a bit that private funders could do here. This is an area in which private funders could take pieces of it and make a really big difference. I'll give you just two examples. I do think that, I'll give you one. In the US, options for storing carbon in cropland soils are relatively well understood. There have been literally hundreds of multi-decade-long experiments that show how to do this. It can always be improved, but we know how to do it pretty well. In contrast, there's been much less work on grazing lands. And grazing lands occupy more area in the US than croplands. And so it would be really interesting to have a parallel development on grazing lands. And it's of a scale where an NGO group who was interested both in land and in carbon could, I think, fund a useful program that produced actionable policies within 10 years' time.
Rick, is there anything you want to add about how you hope this report?
Yeah, I would just say that my hope is that this will lead to a global mission innovation for carbon dioxide removal or NETS technologies in some fashion. And I just note that, at least in the limited surveying that I've done, I have not identified much in the way of government investment specifically in NETS R&D. There's a £10 million effort in the UK, and I'm sure there's some other smatterings of funding here and there in the European Union and perhaps funding buckets that I haven't uncovered. Would be interesting, by the way, to surface whatever folks are aware of, anyone participating on this call or in the network that Simon has so helpfully organized. I think it'd be useful to start tracking those R&D investments which are most relevant to NETS technologies. And above all, I think that the recommendations of the report of the need to scale that quickly are very much well taken, and I'm glad to hear you've had a positive reception on the Hill already. I think that that's a conversation that should be taken to a global scale, though, including by liaising with groups like Mission Innovation and trying to make sure that the European Union and even China and India and others are taking part in this effort, since it is so important. And again, it takes decades and decades, even in the best case scenario, to get any of these technologies or mitigation solutions to scale, as we've seen, to gigaton scale, as we've seen with solar or photovoltaics.
As a piece of that global conversation, there's a question in the chat box about the role of the African continent in particular, which raises questions about technology transfer and equity in the entire carbon removal conversation. I wonder if there's anything to be said on that front.
I guess I don't have anything that specific to say about Africa. There are a couple of things, though, that a couple of ways in which Africa is special. Africa is the home of a lot of the increased food demand by mid-century, and so it's sort of the epicenter for the concern about land and about food insecurity. Africa has lower fertilizer use and lower yields than any other place in the world, is certainly of comparable scale. And so there's a lot of work to be done there. And there's the potential that negative emissions technologies could play a significant role in helping to rebuild the fertility of degraded African soils now and to improve them. Africa is also the home of one of the remaining tropical rainforests, and it's thus at risk to the kind of biofuels land rush that Rick spoke about. And so those are the two areas in which I think one has where Africa is special. Otherwise, it's just like every place else, right? It has the potential to do direct air capture. It has the potential to do some reforestation. It has the potential to do some BECCS if you could use waste biomass effectively, and so on.
Rick, I wonder if you might pick up on some of those points, if you're willing, and just say a little more about the internationalization of the conversation in the ways that you were speaking about it, just making sure that the equity consideration is also kept paramount.
Sure, thanks, Simon. I mean, I guess what I would indicate is that we are just beginning this adventure, and it will be something that plays out through mid-century and beyond. I think that the parlous state of the Paris Agreement implementation is indicative of how hard all these equity challenges will be for mitigation broadly defined, including the nets dimension of mitigation. What we can say is that you can imagine that the pressures to go into actual net negative emissions will likely apply first and foremost and probably exclusively to relatively well-off countries. And so just as we're seeing, I think very appropriately, pressure today on those that have the most responsibility for cumulative CO2 emissions to do the most to cut emissions quickly and bear the costs of technology development for global application accordingly, I can expect that that same dynamic would apply once some countries start to hit something approaching net zero and even go net negative. It'll be the rich countries that are capable of and expected to make that happen. At the same time, with the right kind of creativity on the policy and diplomatic front, there may be opportunities for sub-Saharan Africa, for example, to participate in the commercial upside that comes from some of these investments. And so an early indication of where that could start to happen is I was part of the effort to negotiate the international aviation deal in 2016 that is meant to offset international aviation emissions growth from 2020. And that is an area where some of these technologies outlined in the report could start to get piloted in what will be a 2.5 gigaton cumulative offset market over the first 15 years of that agreement. And many of those could occur in developing countries where you could have biomass feedstock that's sustainably produced and then converted into jet fuel, just in the way that Steve alluded to and that the report outlines in detail. So I think that there are opportunities on the investment side, but there's lots of work to be done diplomatically and in terms of domestic policy, and for that matter, just fundamental measurement technologies, so that we know what's going on with land use change globally, and we can implement domestic policies and diplomatic systems that ensure that the biomass scale up goes smoothly.
Right, you may have lost my video, but can you still hear me there, Steve and Rick? Hello.
Yes, I can still hear you.
So let me just ask another question of you, Professor Pacala, if I may. We've heard about some of the general recommendations that were made in the report, but not yet about dollar values attached to them. What's the dollar scale of the research effort?
Well, so one mistake that everyone will make coming to the report is they'll go to our tables, which list the 50 separate research items, and then they'll sum the cost. And if you do that, that's the wrong thing to do, for a reason that I'll say in just a minute. But if you do that, that total ends up being on the order of $1 billion a year in the U.S., which is a big number. Maybe not an inappropriate number given the magnitude of the challenge, but still, it's a big number. The reason it's the inappropriate thing to do is that the research is by and large staged, so that we talk about the research necessary to take a technology like direct air capture from where it is today through to commercial scale application, right? And so there are 4 separate stages, for instance, in the direct air capture work. The first stage is some additional bench studies that look, for instance, for new solid sorbents to be used in the fundamental chemical thing that catches the CO2 in one of the main designs. And if you got the right sorbent, our analysis indicates you could really bring costs down like shockingly down if you got lucky. The second stage is to take materials and processes that are new and to scale them up to sort of 100 kilogram scales, which is what you need to do if you're going to begin to commercialize such a thing. The third stage is a pilot plant that might sequester on the order of 1,000 tons a year, that sort of thing. And then the final stage is a full-blown demonstration plant, pre-commercial thing, 100,000 tons or so. And obviously you wouldn't do all those things simultaneously for everyone. It's possible that some of the firms in the marketplace might be ready to come in at an intermediate stage, but in no sense would you then be simultaneously spending all of that money. You only get to the latter stages if somebody has made real progress on the earlier stages. So the total, if you sort of look at a per annum expenditure, taking all that into account, is a few $100 million a year. That's the scale. I've lost video with both Rick and Simon.
Our video seems to be crashing, but hopefully you can still hear me. And Professor Pacala, your microphone is muted.
Yeah, I can hear you. Yeah, I can hear you. Can you hear me?
Okay, so I'll come back in with just a final question for you, Professor Pacala, before I invite some concluding remarks. There are some questions that are popping up in the chat box about the kind of lower bounds of cost estimates. Can you imagine things coming down to below $50 per ton for large-scale carbon removal along the more speculative pathways that you've been investigating?
So the simple answer is yes. All right, so I'm not overly optimistic that direct air capture will come down substantially south of $100 a ton, but the end members of our analysis are an order of magnitude lower. All right, so they could get really low, at least in principle. If already the existing options, afforestation, reforestation, the soil carbon stuff, those options are already low cost, substantially less, like $20 a ton or less for some of it. Some of it's even negative cost because it has co-benefits. Blue carbon is going to be very low incremental cost, but low capacity. BECCS is, I think, unlikely ever to get substantially south of about $50 a ton. It's currently at 70 or 80. But direct air capture could get low, right? It really depends on undiscovered materials and the ingenuity of a zillion smart people who would take up the challenge. If I have one area where it would least surprise me to be flabbergasted by a discovery, it's in the mineralization area. Somebody might discover something magical there. And right now, as Rick said, there are all kinds of, mining and grinding rocks would have extremely severe consequences environmentally, just because of the volume of rock we're talking about. But there might be a way to bring the atmosphere to the rocks. And if somebody was clever enough, such a thing might be inexpensive, right? So I'll leave it at that.
Thank you very much. Rick, we have about a minute or so for any concluding thoughts.
Thanks, Simon. I think I'll just close by saying I think this is a fantastic contribution to the cause. I appreciate the chance to interact with the group here. And I think that it's going to require a lot more conversations like this to sort out everything from framing and terminology to the right way to advocate for the investment needed to make this happen. But I'll just close with a call for starting as quickly and as scaled up as possible. When you look at the totals that Steve was just referencing for the wish list here, it really is a modest amount when you consider the 10 to 20 gigaton aspiration per year, and you compare that to the over $100 billion that has been spent just to make solar a reality. So, and to be clear, I think the investment in solar was a fantastic bargain for the overall cause. But it just speaks to the scale and duration of the challenge of making all this happen. And so it's great to have this call to arms, and we should all try to rally around it and encourage governments worldwide to participate in the innovation that's required, both R&D, but also the early deployment that helps with the scaling up of these solutions and the learning by doing that's needed to bring those costs down.
Yeah, I just want to riff off of what Rick just said. While I'm an academic, and I believe in academic research, and this report certainly calls for some, it's useful to keep in mind the enormous success we've had in energy technology as a species in the last 15 years. It's an unprecedented period. If you think about 15 years ago, wind and solar were expensive. Now they're the cheapest form of energy in the right place. The reason is that we subsidized them and created a market. The governments acted like an intelligent VC, and it paid off. It paid off spectacularly. The return on that investment is, well, somebody should calculate it. It's going to be astronomical. Gas with carbon capture and storage is an option to back up wind and solar because unconventional gas was, in large part because unconventional gas was subsidized for a 20-year period, creating a market for it and reducing costs until all of a sudden it crashed into the marketplace. Those options didn't exist, didn't come out of thin air. They came out of a subsidy structure that allowed private enterprise to bring costs down. These technologies could benefit from exactly that same kind of program. And I'll leave it at that. And I should say that they would be at least as big as wind or as solar or as unconventional gas if they could be brought to market. So whatever clout you have, use it to lobby for that. Yeah.
Well, we're immensely grateful, Professor Pacala, for your time on the report, of course, and also for your time in joining us today. And thanks to you and thanks to Rick for your comments. This webinar has been hosted by the Institute for Carbon Removal Law and Policy at American University. As soon as we have the recording of this captioned, we'll have it up live on our website. So check back in a week or so if you'd like to share it with others. I'm Simon Nicholson. I'm speaking out of a grey void, so forgive the technical difficulties, but we very much appreciate everybody, your time with us today. Thank you very